Hello everyone, my name is Gabriela Grunfeld. I am from Argentina. I work in collaboration with Professor Germán Lugones. He is working at Universidad Federal do ABC Paulista in Brazil. And today I would like to talk about the role of quark matter surface tension in dense compact star matter under the influence of strong magnetic fields. So, in compact star objects, finite size effects are important for studying some aspects of the neutron star's interiors or crust. And one important quantity is quark matter surface tension, and it's relevant in the following scenarios. For instance, in nucleation, when the density of the core of a neutron star is few times larger than the nuclear saturation density, then it is possible that ionic matter undergoes through the confinement transition to quark matter. In this case, that a hybrid star may form, and this process is expected to start with nucleation of quark matter drops, where the surface tension determines the nucleation rate and the critical size of the drop. Then it is determinant in the formation of mixed phases at the core of a hybrid star. And that mixed phases may arise if the surface tension of the interface is smaller than a critical value that it is about 60 to 100 MeV per Fermi square. Then it is important to study what happened with the most external layers of a strange star that may have a crust with strangelet if the surface tension of that interface is below of 10 MeV per Fermi square. Then what happens if we add the influence of strong magnetic fields, because magnetars have large magnetic fields. It is believed that in the surface, the magnetic field could be as high as 10 to the 15 Gauss. So there are some speculations that the interiors, the magnetic field could reach a value of 10 to the 19 Gauss. So it is interesting to study the behavior of the surface tension at hot and cold, highly magnetized three-flavor quark matter droplets in neutron stars, in protoneutron stars, and the just merged compact star objects that they come from a binary neutron star merger. So let's talk a little bit about the anatomy of compact stars. So here at the left, we have a conventional scenario. Here we have a neutron star with a nuclear crust and a nuclear mantle. Then from that neutron star, if we have a nucleation process, that drop of quark matter may form. So we can find the quark matter interior, and that quark matter phase shares an interface with hadronic matter, and if the surface tension of that interface is small of a critical value of 60 to 100 MeV per Fermi square, this interface could be a mixed phase. So depending on the value of that critical interface, we have a sharp interface or a mixed interface. In the other hand, we have a quark matter and the strange matter hypothesis. So here we have strange quark matter stars. This is a bare strange stars composed by a roughly equal amount of Q, D, and S quarks. And here a strange quark matter star with a nuclear crust or with strangelet crust, because the magnetic fields in the surface is very high and can support in nuclear crust or strangelet crust, and in this case, depending on the value of the surface tension. This strangelet crust is formed by strangelets or strange quark matter nuggets, which are positively charged, that are immersed in a negatively charged sea of electrons. So the quark matter surface tension value is still uncertain. Its calculations span a wide range of values. Some of them are listed here. The smaller one comes from MIT bug model calculations. and the higher ones from an ambitional Lasinia model. So still the nature of a quark hadron interface in hybrid star, or the strangelet crust in strange quark matter stars, or quark matter nucleation rate is still uncertain, and so far nothing is written in stone. So here in our work, we are going to combine and include the following ingredients. So we are going to start from a relativistic free gas composed by U, D, and S quarks. We are going to add electrons, and we are going to consider the system at finite temperature and density, and we are going to include neutrinos through the chemical potential of the neutrinos. Then we are going to consider a strong magnetic field, a constant magnetic field, and that would give a pressure anisotropy. We are going to include finite size effects throughout the multiple reflection expansion formalism. And we are going to calculate the surface tension that will have an anisotropy as well. And we are going to consider, as I mentioned, 3 different scenarios: the neutron star, proto-neutron star, and binary neutron star merger. That means the just merged compact star objects. So here the formalism, as I told you, we are going to consider Fermi gas, U, D, and S quarks with a multiple reflection expansion, with high magnetic fields, temperature, finite density, neutrinos. We are going to pose electric charge neutrality and chemical equilibrium and beta decay. So in this multiple reflection expansion formalism, the thermodynamic integrals contain modified density of states. Here, the modified density of states. And this modified density of states in a certain region of very small momenta becomes negative. So the theory needs an infrared cutoff. Okay, moreover, our quark matter is immersed in a magnetic field, a constant magnetic field that it is pointing in Z direction. So the transverse motion of the particles with electric charge is quantized into Landau levels. So here we have the momentum, and here we have the thermodynamic integrals. So the transverse and the longitudinal thermodynamic potential of the magnetized quark matter drop, it is displayed here. Here we have the parallel and the transverse one. And we have F and F tilde, that they are Fermi-Dirac distribution for particles and antiparticles. So if we replace in each integral the modified density of states, we can write the parallel and transverse thermodynamic potential in having two main components. The surface, one that it is proportional to the surface and the other one proportional to the volume. So this is the pressure, the modified pressure in the multiple reflection expansion formalism, and this is the surface tension. Alpha is the surface tension. So here the explicit forms for the modified pressure and surface tension, and the total surface tension, the parallel one and the perpendicular one or transverse one, are the summation of all of them. For U, D, and S quarks plus electrons, and the neutrinos have vanishing surface tension because they are assumed to be massless, and the surface tension depends, and all these integrals depends on the mass. So, as I already mentioned, we are going to consider that quark matter is electrically neutral. It is an equilibrium under weak interactions, and chemical equilibrium is maintained by weak interactions among quarks. So here we have the conditions, and we are going to consider 3 different astrophysical scenarios characterized by the temperature and the neutrino chemical potential. That's 3 different scenarios. So for cold, the leptonized neutron stars, we have that the temperature is almost 0. We consider 1 MeV. And we have no neutrinos trapped in the system. I mean, the neutrino chemical potential is 0. Then we are going to consider hot lepton-rich protoneutron stars with a representative case of with temperature of 30 MeV and neutrino chemical potential 100 MeV. So we have a neutrino trap in the system. And the just merged compact object from a binary neutron star merger. That's a limiting case. We consider the temperature of 100 MeV and the neutrino chemical potential the highest of the three, I mean 200 MeV. So here are our results. So in the left side here, we display the parallel and perpendicular surface tension as a function of the density, baryonic density. This is for 0 temperature and no neutrinos trapped in the system. So we took different values for volume over the surface. This is our parameter, 10, 100, and infinite, the bulk. And 3 different values for the magnetic fields that are here. Approximately the lower one is 10 to the minus 4 GeV square, the medium one 10 to the minus 3 GeV square, and the higher one 10 to the minus 2 GeV square. So we can see that for parallel surface tension and for transverse surface tension, when we increase the density, both surface tension, the parallel and the perpendicular increase. This is one result. The other one, it is that the surface tension is a bit insensitive to the value of the value of the size of the system. And it is important to notice here that for parallel surface tension is increasing with the value of the magnetic field, and the transverse surface tension is decreasing with the increasing of the magnetic field. And another important issue is that for fields that they are lower of 10 to the minus 3 or lower than this medium value, I mean all the results are in coincidence. So it is a little bit insensitive to that to the value of the magnetic field when the field is lower than 10 to the minus 3 GeV square. Here in the right side, we have to be careful because in these panels we took fixed number for the density. Here, like 2 times the nuclear saturation density, and here almost 4 times the nuclear saturation density. So let me show you here that here we display the parallel surface tension as a function of the temperature. So for these 2 values of the density, and here we took the same values for the size of the drop that in the previous case with no temperature, and we add here, I mean we add the temperature obviously, and we add here the 3 values for the neutrino chemical potential. So you can see these dashed lines here. So the dashed lines, these horizontal lines, corresponds to a surface tension of 10 MeV per square Fermi. So this will be the limiting case for having a strangelet crust. So that strangelet crust may appear if the surface tension is less than 10 Fermi per square Fermi. And for these lower values for the magnetic field, because the higher ones would correspond to an interior of a compact star. So here we can see that it is possible to have up to, let's say, 100 MeV, up to 100 MeV for 2 times the nuclear saturation density. We may have a strangelet crust in a strange quark matter. In all the cases, except in this one, that, okay, this is more or less about that one. But for temperatures above 100 MeV, the surface tension is increasing. All the values here displayed here, the surface tension is a maximum value for the surface tension is 25, 25 MeV per square meter. So let me show you the conclusions. So for densities from 2 to 10 times the nuclear saturation density, the surface tension lies in a range of 2 to 25 MeV per Fermi square. The larger contribution comes from the strange quark. I mean, the contribution for U and D is smaller, and it is not shown here, but you can see from our article that alpha S is insensitive to V over S, but it is relevant for U and D quarks. The surface tension is unaffected, as I told you, for lower magnetic fields, but for higher magnetic fields, the parallel surface tension is increasing and the perpendicular or transverse is decreasing. And for fixed values of the density, temperature, size, and magnetic fields, we could see that the parallel and transverse surface tension are decreasing with the neutrino chemical potential. That implies that the mixed phase is favored by neutrinos. So according to this model, the hadron-quark interface in hybrid magnetar would be a mixed phase with global electric charge neutrality that should be imposed. I mean, we impose here local charge neutrality, so this is missing here. And the same for strangelet. I mean, we may find a strangelet crust that may form in strange quark matter stars, but still we have to impose global electric charge neutrality. As well, here we impose a local one, but I mean, as a first approximation, we did this calculation, and we believe that this is not going to be very much modified, but we still have to see, huh? I mean, we don't know. And quark matter nucleation is more prone to occur in lepton-rich objects that encode the leptonized neutron stars. So this is all for today. Thank you very much for your attention, and thank you very much, the organizer, for inviting me.